Hello grade 12s. In this lesson we apply the equations of motion to solve the problems about projectile motion. Let's join Scie as she reminds us about these very useful equations.
Equations of motion are great for doing calculations. Let's look at the equations that you have learned for horizontal motion, because we can apply them to vertical motion as well. The three we are going to use are: final velocity is equal to initial velocity plus acceleration times change in time. Final velocity squared equals to initial velocity squared plus 2 times acceleration times the change in displacement. Change in displacement equals initial velocity times change in time plus half times acceleration times change in time squared. Vf is final velocity measured in meters per second. Vi is initial velocity measured in meters per second. A is the acceleration, which is acceleration due to gravity and is a constant value of 9.8 meters per second squared. Delta T is the change in time measured in seconds. And finally, delta Y is the displacement in the vertical direction. When we deal with horizontal motion, then the change in direction is delta X.
It's important to realize that these equations can be used in any interval within projectile motions. In other words, it can apply to an interval in which an object rises in freefall. It can also apply to an interval in which an object drops in freefall, and it can apply to an interval in which an object rises for some of the time and drops for some of the time. We already know that objects in free fall on Earth accelerate at the acceleration due to gravity g, which is negative 9.8 meters per second square. But let's pretend we didn't know this. Let's use the equations of motion and let's calculate the acceleration due to gravity. We'll use the data we get from the lab. Scie, please explain to us how to do this.
We are going to use the motion detector in the lab to investigate the motion of a ball being thrown up and falling down.
Remember that in everyday language, we use the word fall to only mean going down. But in science, this ball is in free fall, the whole time from when it leaves the thrower's hand to when it's caught or hits the ground. This is because the only force that acts on it is gravity. So while it moves upward, it also accelerates in the downwards direction. We still want to calculate the acceleration due to gravity. We are going to use equations of motion. But first we need to get some values to use. Please tell us what to measure and how, Scie.
For this investigation, we set up the motion detector to measure the velocity of the ball at a specific height above the ground. Here's how we did it. Legend threw the ball up, and when it passed the 50 centimeter mark on the ruler, the motion detector gave us the reading of the velocity. The ball reached its maximum height at the top of the ruler, and the motion detector measured the velocity here. When the ball dropped back down again, the motion sensor gave us a reading of the velocity when it reached the 50 centimeter position. When the ball moved up, the first velocity reading was 3.132 meters per second. When the ball moved down, the motion sensor gave us a reading of 3.133 meters per second at the same position. So at the 50 centimeter position, the ball had a very similar value for velocity going up and coming down.
But of course, these two velocities have different directions.
Yes, velocity is a vector, so we need to take direction into account. This is very important. Throughout this investigation, we will take the upwards direction as positive. This is known as the Scienc convention. Any upward vector will have a positive value, and any downward vector will have a negative value. This diagram represents the motion of the ball. Notice that the initial velocity, Vi, is positive 3,13 meters per second when the ball was first thrown up. But the final velocity, Vf, is negative 3,13 meters per second because the ball was moving down.
Scie, this fits in with a discussion we had in another lesson. When we looked at this data for a falling ball, we saw an interesting pattern for the upward and downwards velocity of the ball at the same heights. We noticed that their magnitudes are the same. But now, back to calculating the acceleration due to gravity. We need some more information. The motion detector measures that it takes 0,64 seconds for the ball to move up and down as shown here. So can you see how to calculate the ball's acceleration from this information? Scie, please help us.
Here's a hint. Use one of the equations of motion that are on the data sheet to help you calculate the acceleration experienced by the ball. How did you do, Nombulelo? Were you able to calculate the ball's acceleration?
Yes, but I'm not sure if it's correct.
We'll check, shall we? It's sometimes easier to write a list of the given information before choosing which equation to use. We know that the initial velocity is 3,13 meters per second up, and so the value is positive. The final velocity is 3,13 meters per second downwards, and so the value is negative. The time taken is 0,64 seconds. And what are we looking for?
The acceleration.
Correct. And so we use the equation Vf is equal to Vi plus A times delta t. Substitute in what we know, and don't forget the negative for the final velocity. To solve for acceleration, we need to get A on its own. So now 0,64 A is equal to negative 3,13 minus 3,13. 0,64 times A is equal to negative 6,26. Therefore, A is equal to negative 6,26 divided by 0,64, which is equal to negative 9,78 meters per second squared. If the acceleration has a negative value, what does this say about the direction of the acceleration of the ball? Any ideas, Nombulelo?
I think it means that the acceleration is acting downwards.
Of course. This should make sense to you, as we know that all objects are attracted to the Earth because of gravity. What do you notice about the value we calculated? You would have seen that it is 9,78, which is approximately 9,8 meters per second squared. This is the value for acceleration due to gravity that we calculated in the previous lesson. Now we have seen that when a ball is thrown up, it will experience an acceleration of 9,8 meters per second squared, acting downwards. It will return to its original position at the same velocity that it was thrown, but in the opposite direction.
Now, what if we want to calculate the ball's velocity at its highest point? Whenever we solve problems using the equations of motion, we must choose an interval. For our previous question, we chose the interval shown here. The velocity at the start of this interval is positive 3,13 meters per second, and the velocity at the end of this interval is negative 3,13 meters per second. That is why we called these values V initial and V final. But now we want to calculate the ball's velocity at the highest point. It won't be helpful to use the same interval we used just now. This is because the point we are interested in now isn't one of the ends of this interval. So we can't calculate anything about this point using this interval. But if we use this interval, then the point we are interested in is at one of its ends. So we can calculate the ball's velocity at this point. We call the velocity of this point the final velocity for this interval. Notice that this is a different velocity to what we called the final velocity in our previous question. Scie, please can you help us further with this calculation?
Acceleration of the ball is negative 9.8 meters per second squared. And the change in position between the point we measured, the initial velocity, and top of the ruler, 50 centimeters, which is 0.5 meters up. Now let's calculate the final velocity of the ball at the top of its motion. We use the equation final velocity squared is equal to the initial velocity squared plus 2 times acceleration times displacement, because we have VI acceleration and distance traveled delta y. So VF squared is equal to 3,132 squared plus 2 times negative 9.8 times by 0.5. Then VF squared is equal to 9.809 minus 9.8, which is equal to 0.009. Next, we must take the square root of both sides to find the velocity of the ball at its maximum height. This value for velocity is very close to 0 meters per second, and is probably due to the fact that it is difficult to measure the distance from the starting position to the maximum height accurately. So we concluded from our experiment and calculation that the velocity of the ball at its highest point is 0 meters per second.
So, the ball actually stops. Sure.
Yes, but please take careful note here. Even though the velocity of the ball at the top of its motion is 0, the acceleration it experiences is still 9.8 meters per second squared. The ball is still attracted to the Earth, and thus the acceleration due to the gravity doesn't simply disappear during the motion of an object moving through the air.
That was very helpful, thanks Scie. Please help us with our next calculation. How long does it take for a ball to move from the 50 centimeter mark to its highest point? In other words, what is the time duration, delta t, for this interval?
With all that we know now, we can work out how long it takes for the ball to reach the top of its motion. This time, we'll use the equation. Final velocity is equal to initial velocity plus acceleration times change in time. You see, in this upward throw, the final velocity is at the top of the throw. Substituting in the values we know, 0 is equal to 3,132 plus negative 9.8 times delta t. Therefore, 9.8 delta t is equal to 3,132. Dividing by 9.8 on both sides leaves us with a value for time of 0.3196, which we can round off to 0.32 seconds, correct to 2 decimal places. Do you see how long it took for the ball to reach the top of its motion?
I'm sure that's half the time the ball took to move up and down.
Yes, we've calculated that it took 0.32 seconds for the ball to reach the top of its motion. And earlier we saw that it took 0.64 seconds for the ball to return to its original position, from here to here. If the time to reach the top of the motion is 0.32 and the total time is 0.64, the time taken for the ball to move from its highest position back to its original position must then be 0.32 seconds as well.
Scie has helped us calculate quite a few things about the ball that Legend threw up. Now for our last question for the day. Let's say Legend threw the ball up from here. This time he didn't catch the ball when it passed back down through this height. Instead, he let it fall further. What is the velocity of the ball 1 meter below its starting height? First, we must choose a useful interval. The point we are interested in must be at one of the interval's ends. For example, we can use the whole motion as shown here. For this interval, The velocity we are asked about is the final velocity. We know the initial velocity for this interval is positive 3,13 meters per second, and we know that the ball's vertical displacement is minus 1 meter. This is because the ball ends 1 meter lower than it started. We also know that the ball's acceleration is minus 9,8 meters per second square. We know this because the ball is in free fall throughout this interval. Can you calculate the ball's velocity 1 meter below the mark? Scie, can you please help us?
We'll use the equation. Final velocity squared is equal to initial velocity squared plus 2 times acceleration times displacement. Vf squared is equal to 3,132 squared plus 2 times negative 9,8 times minus 1, which is equal to 9,8 plus 19,6. This is equal to 29,4. We must take the square root of both sides, and the final velocity is equal to positive or negative 5,423 meters per second. However, since we know that the ball is moving downwards, the velocity should be a negative. You should also round off 2 decimal places, so our answer is negative 5,42 meters per second.
Thank you again, Scie. And that was our last calculation for this lesson. Remember to look at the other videos in this series. Why don't you visit the Mindset website at www.mindset.co.za/learn. Goodbye.